Hello everyone, my name is Murali Krishna. Welcome to the part 2 of thermal properties of matter, and this is your channel Acharya Physics classes where you feel the subject very easy. Let's get into the topic, that is the ideal gas equation and absolute temperature, isn't it? So now when mercury thermometer and alcohol thermometer are used to find the temperature of a substances, they may not show same temperature readings actually. What is the reason behind that? We have a reason behind that. So one is different substances are having different thermal properties, right? Different substances are having different thermal properties. And next one is, with respect to temperature, rate of expansion of the substances is also going to be changed. That means if you're trying to change the temperature, rate of expansion of the substances is also going to be changed. That means per degree expansion of a liquid is not uniform at all temperature. Now, readings of different thermometers may coincide at standard points but may vary at other temperatures. Due to this, these thermometers are no use when accurate temperature is needed. And in this situation, experimentally shows that readings of gas thermometers are independent of gas used in it, isn't it? So it is independent of gas used in it, right? So that's why gas thermometers are more reliable to measure accurate temperatures, isn't it? Right? So that gas thermometer works on the principle of ideal gas, right? Let's see what about ideal gas. So this is a Boyle's law states that P is inversely proportional to volume at constant temperature, and based on this we are able to write, so PV, that is PV is equals to constant, and here Charles law states that so V is directly proportional to temperature at constant pressure, isn't it? So by combine, now you can write it as V by T is equals to constant. By combine these two equations, we can write PV by T is equals to constant, isn't it? PV by T is equals to constant. This PV by T is equals to constant, that is what we call ideal gas law. Let's come to the generalized equation of ideal gas equation. Right. Here I am giving that generalized ideal gas equation, that is PV is equals to NRT. Directly I am writing that. So here N is number of moles of a gas. Now here R is a real gas constant. That value is 8.31 joule mole inverse Kelvin inverse, isn't it? Right. So, and now in our previous session we have discussed about constant volume gas thermometer. That constant volume gas thermometer works on the principle of ideal gas law. That is PV is directly proportional to temperature. When volume of the given sample is a constant, so pressure changes linearly with the temperature. And experimentally, all gases at a low density exhibit same expansion behavior, isn't it? Let's take a graph for low density gas. Here I am taking a low density gas, this is, and for low density gas we'll get perfect straight line like this, isn't it? And this is a temperature pressure graph, and if you extend this line towards a negative temperature and this line is coincide on horizontal point, that point is at minus 273.15 degree Celsius, isn't it? Let's take a more low density gases. isn't it? So now here I am taking one more gas. So this is, and this is a low density gas, so that's why it will get a perfect straight line. Now if you extend this line towards the negative temperature, and it is also mid at point of minus 273.15 degree Celsius, minus 273.15 degree Celsius, and these minus 273.15 degree Celsius designated as 0 Kelvin by Lord Kelvin, isn't it? 0 Kelvin by Lord Kelvin. What is the reason behind that? What is the reason behind that? Actually, at this temperature, kinetic energy of the molecule is going to be 0. As a result, that molecules settle in a bottom of the container. So because of that, so pressure exerted by them is reduced to 0. So that's why the Lord Kelvin designated minus 273.15 degrees Celsius as 0 Kelvin, isn't it? So now let's come to the absolute temperature. What is meant by absolute temperature? What is meant by absolute temperature? And here I have given a new scale. That new scale is known as Kelvin temperature scale. Kelvin temperature scale. Kelvin temperature scale, isn't it? And this Kelvin temperature scale is also known as absolute temperature scale. Absolute temperature scale. Absolute temperature scale. And 0 of this scale is known as absolute 0. 0 of this scale is known as absolute 0. Absolute 0. And temperature of the any body on this Kelvin temperature scale is known as absolute temperature, and that is what we call absolute temperature. Temperature of the any body on this Kelvin temperature scale is known as absolute temperature, isn't it? Right? So now and now this Celsius scale has 100 divisions, and Fahrenheit scale has 180 divisions, and this Kelvin scale has 100 divisions, and Reamer scale has 80 divisions, and Rankine scale has 212 divisions. 212 divisions. Right. So now I will give you one formula. Based on that formula, we are able to convert any type of scales to other scale. Any types of scale to other scale, isn't it? So that is TZ minus LP by UP minus LP, isn't it? Here UP means Uttar Pradesh, not Uttar Pradesh. UP means upper point, right? So TZ means given temperature, right? Given temperature scale minus lower fixed point by upper point minus lower fixed point is equals to temperature of the unknown scale minus lower fixed point by upper fixed point minus lower fixed point. By using this generalized form, we are able to convert any type of scales to other scales, isn't it? So now let's see a conversion Celsius to Fahrenheit. Celsius to Fahrenheit. And now, so temperature of the given scale is Celsius and temperature of the unknown scale is Fahrenheit, isn't it? So now temperature of the given scale, so that is a TC minus lower point of Celsius scale is 0 and upper point is 100 minus 0 is equals to temperature of the unknown scale, that is a Fahrenheit scale, TF minus lower point of Fahrenheit scale is 32 degree Fahrenheit by upper point of Fahrenheit scale is 212 and lower point of Fahrenheit scale is 32, right? So now based on this we are able to write TC by 100 is equals to TF minus 32 by, so that is a 180, and now this is a 5 and this is a 9. So now we are able to write 9 by 5 TC plus 32, that is equals to TF. By using this formula we are able to convert Celsius scales to Fahrenheit scale. Celsius scale to Fahrenheit scale. Let's take a one more. So that is right. So now Celsius to Kelvin. Celsius to Kelvin. Right. So now given temperature scale is Celsius and unknown temperature scale is Kelvin, isn't it? So now given temperature scale, that is a TC minus lower point of Celsius scale is 0 by upper point of Celsius scale is 100 minus lower point of Celsius scale is 0, that is equals to temperature of unknown scale, that is Kelvin scale, minus Kelvin scale lower point is 273.15 Kelvin by upper point is 373.15 Kelvin minus 273.15 Kelvin, isn't it? So based on this, so that is a T K is equals to, will get TC plus 273.15. So that is what the value in Kelvin. Let's take an example. So if you want to convert 60 degrees Celsius to Fahrenheit scale, so in that case, no need to follow this formula. You just go through this. Temperature of the given scale is 60 minus lower point of a Celsius scale is 0 by upper point is 100 minus lower point is 0 is equals to temperature of unknown scale is TF minus temperature lower point of Fahrenheit scale is 32 by upper point 212 minus lower point is 32, right? So if you solve this one, you'll get 140 degree Fahrenheit. 140 degree Fahrenheit. That means this 60 degree Celsius is equals to 140 degree Fahrenheit. 140 degree Fahrenheit, isn't it? Right. Here I have given two problems. So here it is. A platinum resistance thermometer has resistance 2.2 ohms at 0 degrees Celsius and 5.6 ohms at 100 degrees Celsius. And now, if resistance is 7.3 ohms in a bath, find out temperature on platinum resistance thermometer. Right? So that is what the question here. Now, so if you want to find out temperature in platinum resistance thermometer, as we know that, so that is R minus R naught by R100 minus R naught into 100. So here already they have given resistance value, that is a 7.3, right? So at a temperature T, so that is 7.3 minus initial resistance of the platinum resistance thermometer, that is R naught. So that is R naught value is 2.2 ohm. 2.2 ohm by, so here resistance at 100 degrees Celsius, so that is 5.6. Resistance at 0 degrees Celsius, that is a 2.2 into 100. So now if you solve this one, we will get 150 degree Celsius. 150 degree Celsius, isn't it? Now let's come to the next question. So that is, the pressure of air in a bulb of constant volume gas thermometer of 0 degree Celsius and 100 degree Celsius are 73 centimeters of mercury and 100 centimeters of mercury respectively. Calculate pressure at a room temperature 20 degrees Celsius. At 20, so here at 20 degrees Celsius we have to find out pressure. We have to find out pressure by using constant volume gas thermometer. As we know that in constant volume gas thermometer we use pressure as a physical quantity to measure the temperature, right? So now that is T is equals to P minus P0 by P100 minus P0 into 100, isn't it? As we know that T is equals to, T they have given in the question itself, that is at 20 degrees Celsius, that is equals to, so pressure at a room temperature 20 degrees Celsius here, so that is this P we have to find right now, P minus at 0 degrees Celsius, pressure is 73 centimeters of mercury, so that is a 73 by, at 100 degrees Celsius pressure is 100 centimeters of mercury, so that is 100 minus 73 into 100, isn't it? Now based on this 20 and 5, so now we are able to write 27 is equals to 5p minus 365. So based on this we are able to write P is equals to 392 by 5 centimeters of mercury. mercury. This is what the pressure at a temperature 20 degrees. Right, here I have given one more problem. So that is, two ideal gas thermometers A and B use oxygen and hydrogen respectively. The following observations are made. Temperature. So this is a temperature column and pressure at a thermometer A, pressure at thermometer B. And this is a triple point of water and this is a melting point of a sulfur. Triple point of water and melting point of a sulfur. Right. So triple point of water, already we know the temperature of triple point of water. So that is a 273.16 Kelvin. That is 273.16 Kelvin. 273.16 Kelvin. Isn't it? Right. So now at that temperature, so pressure at thermometer A, so that is 1.250 into 10 to the power of 5 Pascal, isn't it? Now at this temperature, pressure of thermometer B, so that is a 0.2 into 10 to the power of 5 Pascals. Likewise, here I have given those values, isn't it? So what we have to find, what is the absolute temperature of normal melting point of sulfur as read by the thermometers A and B, isn't it? And take a solution. So as we know that triple point of water is equals to 273.16 Kelvin. 16 Kelvin. So as we know that gas thermometers works on the principle of ideal gas law. So that is PV is equals to nRT. Here you can take N, R and V as a constant, then you are able to write P is directly proportional to temperature, and now from this you can write P by T is equals to P1 by T1 is equals to P2 by T2. So for oxygen thermometer, that means for thermometer A, you can write, so that is a P triple point by T triple point is equals to P melting point of sulfur by melting point by T melting point. So here we have to find out melting point temperature of a sulfur, isn't it? Now that is a T MP is equals to, so that is a PMP by triple point pressure into 273.16 Kelvin, isn't it? 16 Kelvin. Now where is the chart, please? Right. So now, so here you can substitute 1.797 by triple point temperature is 1.25 into 273.16 Kelvin. 273.16 Kelvin, isn't it? So if you solve this, you will get 392.69 Kelvin. Sorry, I got some camera problems. Right. So now, if you follow this same method for thermometer B also, we'll get 391.98 kelvins. We'll get 391.98 kelvins. If you observe these two values, we got some slight difference, right? Why you got that slight difference means, actually those hydrogen and oxygen, those are not perfectly ideal gases. So that's why we got some slight difference between these two melting point of temperatures, isn't it? Now, if you want to reduce the difference, you have to take those gases at low temperature and high pressure, isn't it? Thank you.